Hello, this video is section 3.3, the addition rule for probabilities in the Larson book. So let's get started. First thing we're going to learn here is mutually exclusive. What does that mean? Two events A and B are mutually exclusive if A and B cannot occur at the same time. So let's look at a couple of examples with your standard card deck and rolling a single die and see if we can kind of grasp this idea. It's not too bad. Draw a card out of a deck, and you let event A be drawing a 4, and you let B be drawing a 7. So what you're looking at here is if those two events can happen at the same time, it's possible for them to happen, that means they're not mutually exclusive. If they cannot happen together, they are mutually exclusive. Therefore, it is impossible to draw a card out of a deck that's both a 4 and a 7. So these events, A and B, would be mutually exclusive. Next example, drawing a card again, drawing a queen, drawing a heart. So we have to ask ourselves, is it possible for a card to be a queen and a heart at the same time? And the answer is absolutely yes. It can be a queen and a heart. So the fact that they can coexist, that means those events are not mutually exclusive because they can happen at the same time. Roll a single die. Let E be rolling an even number, and let F be a number greater than 4. So is it possible for a roll on a single 6-sided die, you're counting the dots facing up, rolling an even number and rolling a number greater than 4 at the same time? Now, greater than 4. Absolutely. There's only one event that would do that. It's a 6. A 6 would be both even and greater than 4. But the fact that there's at least one or more event things where it can happen at the same time. Therefore, once again, they are also not mutually exclusive. Wonderful. The addition rule for the probability of finding A or B. So now we're dealing with ORs. We've dealt with AND in the last section, dealing with ORs. So the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. And we're going to see why that's necessary here in a minute. However, if they're mutually exclusive, the probability of A and B would be 0, because if they cannot occur at the same time, the probability would be 0. So then the equation just reduces to just probability of A plus probability of B. You could still, use this top equation every time and just, then use 0 for the probability of A and B part. So anyway, you don't have to use two separate equations here. So let's take a look at this example. Roll a single die. Find the probability of rolling a number divisible by 3 or rolling a number less than 4. So we're looking for anything where one or the other. See, and always means they both have to be true at the same time, but or means one or the other. So, so the way we calculate this is, so I listed them out, and roll a number divisible by 3 would contain the events of 3 and 6. Less than 4 would be 1, 2, and 3. So the probability of A rolling a divisible by 3 would be 2 out of 6, because there's 2 outcomes. So it's 2 out of 6. Less than 4, 1, 2, 3 would be 3 out of 6. Now, the subtraction part. Are there any elements that are in common between these two groups? Yes, there are. These are not mutually exclusive because they both have 3 in there. So we have to subtract off the 3, which has a probability of 1 out of 6, and then we get 4 out of 6 equals 2/3. So the subtraction is in there to prevent basically what's known as double counting, because A or B, you don't want to count that 3 twice. And then obviously you won't be always doing these problems where you have a list of numbers like this, but the subtraction is to get rid of something counting more than once. So you wouldn't want the 3. So really the idea is what satisfies this is either 1, 2, 3, or 6. There's 4 items. So that's the purpose of the subtraction. 4 over 6, which then of course would reduce to 2/3. We select one card from a 52 card deck at random. Find the probability that we draw a king or a red card. I guess I could bring up the card deck to look at here. All right, so there's our deck of cards. We'll keep that up there handy. And obviously you'll be able to keep that handy for any time you're doing anything. Probability of drawing a king or drawing a red card. That means you're looking at your card. It's at least one of the two, or if it's both, it just counts one time. You know, if it's king and red, we count it as once. So probability of A, drawing a king. 4 kings in there. One, two, three, 4 kings. I'll go back to the problem in a minute, but I'll go explain it while I'm here, so I don't have to go back and forth. Red card. Probability of drawing a red card. Hearts, 13 hearts, 13 diamonds. That means we have 26 red cards. Now the $1,000,000 question here, if they're mutually exclusive or not. Because if they are mutually exclusive, it would be, we don't have to subtract anything, but if they aren't, we have to subtract the ones that were counted twice. So all you have to ask yourself is it possible for a card to be king and red at the same time? If so, how many cards satisfy that? And that would be 2 of them. The king of hearts is a red king. The king of diamonds is a red king. So we have to subtract off those 2 red kings because they've been counted twice. They were counted as kings and they were counted as red cards, and we only want them to count once. So we come over, let's look at the problem. So then there's the 26 over 52 for the red, and there's the minus 2 over 52. We had to subtract the cards that were both king and red. Get 28 over 52, that reduces to 7 over 13, and the homework's probably going to be a decimal answer, which is perfectly fine. So I'm just not putting the decimal answers there, you know, but obviously that doesn't take too much ability to take the calculator and go 7 divided by 13, so yeah, I think we can handle that. Here's another one. Queen and an ace. So we want to find the probability of drawing a queen or an ace on a 1-card draw. So what do we got? Let's see. I'll just bring this back up here. Queen, we got 4 queens. Ace, we got 4 aces. Is it possible for a card to be a queen and an ace at the same time? And the answer is absolutely not. It cannot be a queen and an ace at the same time. So, you know, you can either subtract off 0 or just ignore it, you know, basically. I'm just pointing out because these events are mutually exclusive. So it'd be 4 over 52 plus 4 over 52, no double counting, so there's nothing to subtract. You get 8 out of 52, 2 over 13, and whatever the decimal equivalent of that is. Wonderful. All right, now we got, okay, one of these little row column charts here. So like we've done with conditional probabilities, we can now do these. Oh, actually, I see a question here that has conditional in it. That's good. It won't hurt us to look at another conditional real quick. But now we can do these ORs, the addition rules. We can also do these on here. All righty, let's see. Probability of bachelor's degree. So that's just going to be, that'll be out of your grand total. And how many of those were bachelor? So there it is, 1399 divided by 2671. Now the conditional, probability of bachelor's degree given that the person is female. So that means we're only dealing out of the females. That's our total. We reduce the total to just the females. And out of those, how many were bachelor degrees? 804. So you see I have 804. then divided by 1561. Wonderful. Oh, here's another given, but here comes some givens and ors mixed in here. But that's okay. We're going to look at all of them. Bachelor's degree, given that the person is not female. Well, I'm going to assume not female means male. So out of the males, 1110, bachelors, 595. So there's 595. What did I say? 11. Oh, that's why this is wrong. Let's see if I can tweak this without a stylus here and try to. I just copied. Dang, I did it a couple other times too. Some reason I just misread it. You see, it's 1110. I kept writing 1100. Well, okay, I had the right idea. Okay. We're going to fix that right now. And I'm going to go ahead and fix it for the other one, even though we haven't gotten there yet. Let's do the both of them. So, all right. Let's see. That's going to be 11. Wish I was working on my tablet here instead of this regular kind of PC, but okay, there we go. That 0 looks weird, but at least it's not 3 times as big as the ones. All right, so we got C. D says probability associates or bachelors. Now I kind of grouped these because they're all going to have the same denominator, so I kind of grouped them. So that's I'll explain it here, but I'm going to leave it written like that, but I'll explain it. Associates or bachelors? Now we're assuming they only have this degree. So what you don't, I know it's kind of this example is kind of weird because if you have a master's, you already have a bachelor's. But I think this maybe is just what's their highest degree level they reached. So it doesn't matter if they reached something lower than that along the way. So that's the way you kind of interpret this one. Probably should say highest level of degree, I guess. Or they're saying degree earned in that particular year. Okay, well that's all right then. We don't have to consider any prior. Now notice that. So there's the total, and here's the grand total. Now on these kind of tables, all rows are mutually exclusive, and the columns are mutually exclusive. To be not mutually exclusive, you have to have where row meets column. So these are 2 separate rows. So they're mutually exclusive. The males that earned associates and earned bachelors are mutually exclusive. So you see I have 260. Oh, I'm sorry. I'm not male. Excuse me. Okay, I'll fix this real quick. It's total. I'm sorry. There we go. All right, we got it. You're probably looking at what's he doing there? Sorry. Yes, total associates, total bachelors. Had nothing to do with male or female over total people. So there it is. So it's those 2 numbers added together divided by 2671. So there it is. The next one, earned a doctorate given they were male. So that's a conditional probability. So it's coming from the males. So out of the group of the males, 25 earned a doctorate. So how about 25 over 1110? There we go. Right there. Masters or female. Probability of masters or female. So whenever the ors always come out of the grand total. It's only the givens, the conditionals, where you reduce the denominator. But the or comes out of the grand total like that there. So I already forgot. Female or was it? So, wait, masters or female. Here's your female. Here's your masters. Is it possible to be both masters and female at the same time? Absolutely it is. Right here. So you can see that the total of the females includes that 329. The total of the masters includes that 329. So one of those 329s needs to be removed. Not both, just one of them. Because we want one of them. So that this one, because they're not mutually exclusive, we subtract. So it's 1561 plus 559 minus that 329. There it is. Next one, associate's degree and a male. If these don't intersect, the answer would be 0, but they do intersect. So and ors will always be over the grand total. So and is where row meets column. So associate and male would be right there over the grand total, 2671. Yeah, there's 260 over 2671. What's probably is a female given they earned a bachelor's. So given they earned a bachelor's means we know the sample space is coming from the bachelor's. I'll just copy and move these. I'll have to redraw them. If it let me, let me select it. No. Sometimes it lets me do it. Sometimes it doesn't. Bachelor's. Just for grins, I'm going to try. Oh, okay, let me do that one. So out of the 1399 bachelors, 804 were female. So there it is, 804 divided by 1399. Roll a single die, find each probability. Rolling a 6 or a number greater than 4. Rolling a 6 is 1 out of 6. Rolling a number greater than 4 is 5 and 6. So there's 2 ways to do it. 2 out of 6. Can you get a number that's both a 6 and a number greater than 4? Absolutely. That would be the number 6. So we have to subtract off the probability again of rolling a 6 will be 1 out of 6. So you add these up. You get 2 out of 6, which reduces to 1/3. Rolling a number less than 5 or an odd number. Less than 5, 1, 2, 3, 4, 4 out of 6. Odd number, 1, 3, 5, 3 out of 6. Is it possible for it to be less than 5 and odd? Absolutely. The numbers 1 and 3 would be less than 5 and also odd. So there's 2 of those, 2 out of 6. So you add 4 plus 3 minus 2, you get 5 out of 6. Rolling a 3 or an even number. 3, 1 out of 6, even. 2, 4, 6 would be 3 over 6. Notice I mentioned these are mutually exclusive, meaning it cannot be 3 and even at the same time, so that means there's nothing to subtract. So all that means on these ORs is if it's mutually exclusive and they cannot happen, it means you won't be subtracting anything. I could have put minus 0 there, I guess, but no, I just said it, so no subtraction for that one. So what do we got here? Okay, a couple more things here. 2 dice. We're going to bring that into play here shortly. That could be fun. Here's another chart problem, but there's not as many in this one as there was in the other example, which is probably good. Yeah, here I have them all written as individual fractions. Up there I showed you. You see, if they all have the same denominator, you can just group their numerators together like I did up here for these. Let's see the parentheses here and here. It's the same thing. You can do that if you don't feel like writing. It's because the denominators are the same. That's why you can do that. So what do we have in this table? We've got left-handed people, dominant hand, gender, men, female, men, women. All right, let's see what the first question says. Person is left-handed or a woman? Okay. So, probability of being left-handed, 113 over 1,000. Probability of being woman, 475 out of 1,000. Is it possible to be left-handed and a woman? Absolutely. And there's the number where left-handed meet women, where left meets women, and we have to subtract that number. So it's not mutually exclusive. So we subtract 50 over 1,000, we get 538 over 1,000, which decimal would be 0.538. Actually, that one I didn't really need a calculator to do, but I mean, I'm not saying you shouldn't use one, but yeah, dividing by 1,000 is actually pretty easy. Just moves your number 3 decimal places to the left. The next one. Right-handed or a man? Probability of right-handed, 887 out of 1,000. Probability of man, 525 out of 1,000. Can you be left-handed, right-handed, and a man? So where does right hand meet man? Right there. 462 right-handed men. So that's the number we have to subtract off, over 1,000. 462 over 1,000, and that ends up being 950 over 1,000, 0.95. So we basically have a 95% chance if we pick a person out at random, they're going to be either, it could be both. They're either right-handed or male or both. So that includes all the right-handed females. Wonderful. Part C, a right-handed woman. Okay, that's just going to be just a regular probability question. So that'd be out of the 1,000. No, so right-handed woman. You look where the right and women intersect. 425 out of 1,000. Perfect. Part E says, are being right-handed and woman mutually exclusive? No, because you can be right-handed and be a woman. Alrighty, I'll erase that. Let's jump down here and look at 2 dice. Now, sample space for 2 dice. Now, sometimes if I'm asking people in class, you know, and before I even put it up on the screen, well, if you've got 2 dice, you know, we know there's, you know, rolling 2 dice and there's 6 outcomes on each dice. I'll say how many total outcomes will there be, and sometimes a quick reaction will say 12. They'll go 6 times 2. That's not correct. It's 6 times 6. The 2 comes from the 2 6s. So yeah, so there's 36 outcomes. Here I have them lined up row and column. You know, you can have 1 1 1 2. There's 36 total outcomes on the dice. So there you can keep that handy for you with the kind of questions we're going to ask. So you can refer right back to this chart. Two dice are rolled. Find the following probability. So these are going to be over 36. I don't have any conditional questions. Yeah, I wouldn't ask any conditionals on these. So with no conditionals, either ors or ands or whatever, or single numbers. But anyway, that means everything will be divided by 36. So there's no condition or anything like that. So, okay, well, let's see what we got here. This could be fun. Sum is 9. Got to add up to 9. All right. Kind of crooked there, so unless you see any others, I don't, but those 4 outcomes are the only ones that add up to 9. 6 3, 5 4, 4 5, 3 6. So there's 4 outcomes. So therefore you see what I have right here. Probability you get a sum of 9 is 4 out of 36, which reduces to 1/9, which would then have a decimal equivalent if needed. So there we go. So that's what you're looking for, just things off of here. Sum is 8 or sum is 3? Now, before I think solve this, I'm going to go ahead and mention that sum or 8 sum is 3, they're going to be mutually exclusive. There's no way that two dice can add up to 8 and 3 together. So that's going to be mutually exclusive, so there will be nothing to subtract here. So let me find the 8s and let me find the 3s. So I'll do the 3. It doesn't really matter what order I do them, but here are the 3s. There's only 2 of them. And I'll go a different color for the reds. Red for the 8s. 8s are going to be on this little diagonal pattern right here. I see 2 of them for the 3s, 5 of them for the 8s. Add those together. 5 over 36 plus 2 over 36 is 7 over 36. Part C. Sum is 7 or the first number is 4. Now, one way, if you do it like I'm doing it here, if you take some sort of, I don't know if you're going to bother to print this out, or I guess if you have a tablet can write. You don't have to do that. I'll just show you one way you can look at the mutually exclusive. But doing it this way, yeah, if you can write on your thing, that could work. If you see that these two things don't intersect, that's how. But you can still think through it without doing this. Well, I think you'll see what I mean. Let me show you what I'm talking about. You'll see these two things overlap if they're not mutually exclusive. Sum is 7. Okay. I'll leave that as red here. So let's go. That's going to be 7 is the one out of all the sums that there's the most outcomes of one particular sum. 7 is the most. There's 6 of them. Then it goes down from there. That one. And what's the other one? 4 on the first number. Right here. Excuse me. I was thinking, here we go. 4 on the first number. Yep, well, sorry about that. But anyway, point being is you can see an overlap there, right? If they cross over each other anywhere, that's an overlap. So in fact, it's only overlapping one time, but this particular value, 4, 3, shares the trait of the sum is 7 and the first number is a 4. So we have 6 ways it can be a 7 there in red. We have 6 ways it can be 4 on the first die. And then we have one way that it's both. So we have to subtract that off. So you see it's 6 over 36 plus 6 over 36 minus 1 over 36 gives me 11 over 36. Part D says find the probability that the sum is greater than 9. Right. Let's see. So I'll start with the 9s, and they're going to work their way down to 6. So there are your 9s. But then as you go down around like this, obviously you double check this. When you got that little wedge right there, everything that little wedge adds up. Wait, did it say greater than 9 or greater? I might have missed. Greater than 9, excuse me. I got to start with 10. Okay, that's easily fixed. I misread it as greater than or equal. Yeah, what I was doing was greater than or equal to 9, or greater than 8 would have been right for mine. Greater than 9 means we start at 10. So it's that little triangle. Okay. So there's 6 of them in there that are greater than 10, greater than 9, which means starting at 10 or more. Yeah, so 6 out of 36 then will be 1 out of 6. All right, so that will conclude the lecture, and then now we'll get to the homework. I would like to start with question 3 here in the homework. Let's take a look at this one. A physics class has 50 students. Of those, 14 are physics majors, and a total of 18 are minoring in math, including 2 students that are both majoring in physics and minoring in math. So that means this is they're not mutually exclusive. Find the probability that a selected student is minoring in math or a physics major. Okay. Instead of writing this down, I'm just going to go straight to the calculator on this, and you can obviously you can use Excel as a calculator if you wanted to, but so we have 14 out of 50. Like I say, you'll see the numbers here, so that's just as good as me writing them down. Plus 18 out of 50. Minus the 2 that belong to both. .6. It wants 3 decimal places, so I'll put 0.6. Sometimes whenever it's an exact answer like that, 0.6, it won't care about the extra. I'm not taking any chances. I'm putting the zeros there. Okay. But it certainly cares whenever it's like a rounding thing or something like that. I'm going to skip this one because, I mean, if you need help with it, let me know. But, boy, this is just like right out of the notes I did. They're not the same scenarios. But we did an example right there in the notes on this. Same thing here. Rolling a single die. So I have complete confidence in your ability to do these based on that. Let's find something a little bit different. Oh, okay, here's something with a pie chart. So let's see what that's all about. That'll be different. I don't have that in my notes. But I'm confident we can use our newly found skills and figure this out. What do we have here? Randomly selecting someone who's under 5 years old. Okay, so these are already in percentages, so we don't have to take, if they were individual numbers, like sometimes you may see in pi individual frequency numbers, then yeah, you would have to take the number and physically divide it by the total. But this is better because it's already in percentages. Less work for us. I think 5.1 ought to be. Okay. Oh, move that pie chart up. All right, what am I? Selecting someone who is 45 years old or over what? Let's take a look at this one. So I clicked already on this, and this is number 6. Brings up a pie chart, and the pie chart's already in percentages, so that's good for us in the sense that we don't have to take individual frequencies and then divide by the total, which is just a little extra effort. Under 5 years old, so it's right there. The percentage is right there, 6.2. Check answer. Fantastic. Randomly selecting someone who is 45 years old or over. The wording's a little weird there because the or makes you think it's going to be like an or probability, but it's really just, they should have just said selecting someone who is over 45 years old. They shouldn't have put the or over. That makes it more confusing. So think of it as just being over 45 or 45 or older. Yeah, I guess, well, okay. You know what? They should have said at least 45 years old. Okay. Anyway, it's going to be the bottom three, starting at 45. So I'll put these in here, and I won't worry about percentage. We know the answer is already going to be percentage. So 24.1 is the 45 group, 11.8 next group, and then 8.6. So I guess the 45 or older makes sense, but it's just the or to me makes it confusing because we've been doing, or probabilities. So 44.5, I would have just said at least 45 years old. Excellent. Who is not 65 or over? So what I'm going to do for this one, that means you can add all those bottom ones up, but I'm going to use the complement. You can add up starting at under 5, going all the way to 45 through 64. You can add all those up. But not 65 or over just means I can go 1 minus. Now I'm going to put these in, I can go minus, minus back to back, or put these in parentheses, and I'll just put them in parentheses. So so it's basically the complement. 1 minus, yeah, we're looking for lower than that, so we're doing 1 minus that or older. So plus 8.6. Like I said, you can just add up all those bottom ones. It'll be the same answer. And oh, ha! All right. I see I have to. If I'm going to use percentages, I have to make the 1 be 100%. Got it. All right. Yeah, 1's only good if you're just using, decimal or fraction probabilities. Sorry about that. There we go. 79.6. Well, easily fixed. There we go. Now you'll know, if you look at this, when you do that problem, you won't do that bonehead mistake I just made. Excellent. Oh, still going. Make it stop. Who's between 20 and 34? 20 and 34 would be the 20 to 24, and then the 25 to 34. So that's going to be 5.5 plus 14.9. 20.4. All right, finally. Not that that was that bad or anything. I just was okay. I think I'm going to do this one. I'm just going to look ahead real quick though. Just that looks, yeah, a couple with, yeah. Oh, they were kind of the same thing. Let me just look at the show completed and see what the rest of it shows. Okay, 3 ors there. Okay, these are about the same type of problem, so I'll just do one of these. They're very similar. Just gives you practice by doing 2 of them. So this one I'll just have to bring up the table here. Oh yeah, we had a problem like this for the last section on conditional probabilities. Male or female? No, male or received degree in the field. Male, female, degree in field, degree outside of field. Now I'm going to do the thing I'll show you, especially because these numbers are large too. I don't want to be writing every fraction over 1.75624. So I'm going to put all the numerators together and then in parentheses, and I'll divide by that number like I did. Well, actually, this would be more efficient to do this in Excel. It just, not that we're using any fancy features, it's just I can cell reference it real easily, then type it in the calculator. But I mean, using the calculator is fine. So back to the question. Yes. I'll just snip it out so that way I don't have to keep going back and forth so I don't mess up here. I'll put it on the spreadsheet. That way I can look at it and you can look at it. we can all look at it. So I'm going to say, once again, I can still group them together. I can go equals my numerator male, which will be the total males will be in position D2. It's a 768,000 number. If you prefer to use a calculator, I'll just say it out loud there. Or degree in field will be that bottom number right there, 321. So it's B4. If I don't want to type the number, but you might go, hey, if you'd rather type the numbers, you do what makes you happy. Is it possible to be a male and to receive the degree in the field? And it certainly is. Oh. All right. I guess I can't just highlight stuff just yet. So until I get the formula. But anyway, yes, I want to subtract the B2, the 177,000 number. That's the one where it's male and degree in field. Oh, a minus would help. B2. Now I can close that off and then all divide by the big denominator, the 1756, which is located in D4. And if I type it right. So what's the rounding? And 3. 5195 will be 520. Like I said, you can format it to show 3 decimal places if you don't want to think about it. So I'm going to go 520. Got it? Yeah, just so I don't mess this up, I'm going to snip it over every time there too. I think that's good. So that way you can see it when I'm doing it also. Oh, I know what I want to do also when I get back to the spreadsheet. I want to put, so you can see this, I want to put the formula text. So you can then look at that and pause it. And it's in B9. Yeah, so that way you can now see that if you couldn't quite catch what I was following. And yeah, that way you can freeze that and pause it and look at it and look and see what cells, what numbers are there in and everything. So tremendous. So I'm going to copy this little formula text right down here, because this is about where I'm going to do this problem to the left right here. Female. Where are my females? Right there in D3. So I'm kind of using the same kind of idea again. D3 is my female total. Plus, receive the degree outside of the field, which will be this number right here, C4. Is it possible to be female and receive the degree outside of field? Absolutely. It's that number right there above it, the 843 number. Female and degree outside of field, that is cell C3. And then we still divide by that same D4. So assuming it's 3 decimals again, I'm going to go with 899. Good job. Female or not female? Oh, they tricked us. Could have been nice and just said male. Okay, so watch for that kind of mess there. Tricky stuff. Not female or degree outside the field. All right, that's kind of almost caught me there. Surprised I haven't had one. I'm going to look at the next one. I was waiting to see if they were going to do one that was mutually exclusive or not, but they haven't yet. That's okay. I was just curious. Let me zoom out just a little bit here, maybe, so I can. Yeah. I can scroll back up there. It's no big deal. equals, parentheses. Not female means our males. Total males, D2. Plus, outside a field, C4. Minus, can you be male and receive degree outside a field? Absolutely. That would be right here in cell C2. Like so, divided by D4. There we go. So if I did this right, be rounded would be 0.582. All right, what did I do wrong? Not female or received a degree outside a field. Ugh. A smell. All right. Ah, okay. Oh, okay. I'm off. It's the second thing here is C4. It looks like I put C3 in there. Okay, that's easily fixed. That should be it. Yeah. 918. Well, okay, we were able to correct that pretty well. Let's make sure I get the check mark before I get too cocky here. But I feel confident since I saw the error. Unless I made more than one error, but okay. All right, so that takes care of this question. And that will end this video on 3.3, the addition rule.